Okay, in this lecture, I'm going to show you guys how to program stepper motors. So I know this is a pretty topic of high interest, so I'm going to show you guys a good example of how you can do the calculations required for programming the stepper motor, as well as writing some simple functions to cause it to move in different directions with different speeds and different angles and things like that. So hopefully this is pretty useful. So really, ultimately, what we want to do is we want to be able to control the stepper motor, right? We want to make it move a number of degrees. Um, so we need to be able to translate, um, you know, numbers of pulses to degrees of motion in the stepper motor. But also, if we want to make it move at a certain rate, that's going to require a little bit more of these calculations, so we know how fast the pulses need to come to cause the stepper motor to move at a certain degrees per second rate, right? Okay, so all of these things are basically controlled by the characteristics of our PWM waveform, right? So our PWM waveform, we're going to have pulses coming in. The duty cycle, doesn't really matter for the stepper motor as long as these pulses are wide enough for the driver to accept them. We've got a couple of different things to think about here. We've got, what characteristics do we have of this? We have the overall pulse period, right? Oops, that's not right. Okay, so that's the period. We have our duty cycle, right, which is controlled by our pulse value, okay? Where duty cycle equals pulse divided by period, okay? So, and these are controlled by, well, your pulse is a certain value you program in. Period, is going to be related to the speed that your basic time unit is counting, as well as the number of counts in your period, right? So remember, this basic time unit is continually kind of counting up and resetting, right? Something like this, and it's hitting this ARR value, right, that we program. And then we have, at this point, we have, counts per second. Which is our counter clock. And that's going to be a function of the APB1 or APB2 system bus and our prescaler, right? So that's going to be like our bus clock divided by prescaler plus 1, right? Okay, so that's the counter clock. And then the ARR is going to be a number of, ARR is the number of these pulses that it's going to count to, right? Okay, so just kind of setting the stage and the terminology for the things we need to figure out. Okay, so before we do that, let's take a quick look at the hardware and look at the setup. Okay, so here we have a little demonstration of the stepper motor working. I put a little sticky yellow arrow on here so you can kind of see what it's actually doing, but basically we're executing, I think, 4 commands here. We're rotating certain numbers of angles at or degrees at certain speeds. So you can see the first one is about at 180 pretty fast, then it goes back about 135 degrees, then it goes pretty quick to another 45 to the right, and then slow 90 degrees back to where it started. So kind of just a repetitive pattern to show that we can basically issue these commands to the stepper motor that'll make it go a number of degrees at a certain speed and in a certain direction. So as far as the hardware setup, we have the microcontroller over here, and we have a stepper motor driver. It's a pretty typical chipset stepper motor driver. Then over here we have a level shifter, because the GPIO on the microcontroller puts out a 3-volt signal, but these drivers really require 5 volts. So I have a basic level shifter here that it's something you can get. I think you can get several of them for about $10, and it basically is just a bidirectional translation between 3 volts and 5 volts, or between 2 voltages. It's pretty much made for translating 3 or 3.3 to 5 volts. So here I have 3 volt signals going from the microcontroller into this translator, and then from this translator I have them going back out to this this driver. Okay, so the driver is basically taking in inputs of pulses, direction, and enable. I'm not using the enable, so it's always turned on, but I am driving the direction and the PWM pulse input, from this microcontroller, and ultimately from this translation device. Okay. So the driver is also connected to the stepper motor. There is 4 connections to the stepper motor. It's basically your A and your B phases. So you're basically just driving current through coils in the stepper motor, and that's pretty much what the driver is actually doing. It's translating these pulses to some sort of a micro step. There are some dip switches on the side here that you can't really see, but these configure your stepper motor. So I have it configured a certain way. I think I have it configured for 1600 pulses per revolution. Okay, and then over here you can set kind of the drive current, which I have it set pretty low because we're not really moving any loads. So I just wanted to keep it pretty basic. Okay, then of course for the stepper motor over here. Okay, so it's pretty simple hardware setup. So really what we need to try to do here is we want to write some code for the microcontroller that we'll be able to write a function that we can make this arrow move a number of degrees at a desired speed and in a desired direction. So that's going to require figuring out basically how many pulses are going to make it move how far, and how fast do those pulses need to come to make this move a certain degrees per second, right? So it'll be pulses per degree we need to figure out. And that's pretty easy, since we know right now it's about 1600 pulses, or 1600 degrees, or steps per rotation. So 1600 pulses required to move at 360 degrees. So we can do that math pretty easily. The speed's a little bit more difficult to calculate, because we have that's dependent on the base time unit of our timer, which is going to be impacted by the ARR and the prescaler and the clock on that timer bus. Okay, so let's go through and kind of write this code as an example, and it'll just give you one example of how we can program stepper motors. Obviously there's many ways to do this. This is just one way to show you, basically to go through the calculations. I think it's pretty helpful, and just show an example of how we can write a function to accomplish this. Okay, so a few things we need to figure out. Like I mentioned in the hardware demonstration, we have the stepper motor set to 1600 pulses per revolution, right? So 1 revolution per 360 degrees. So we want to do degrees. Let's say we want to calculate degrees per pulse. Let's back up. Or pulses per degree. Okay. it's going to be 1 revolution per 360 degrees. Can't write today. Right? Times 1600 steps per revolution. Okay, so that's the driver setting right now for the stepper motor. Okay, and then we can say 1 pulse per step. So this is, I'm sure you guys have used this method, but when you try to do some of these calculations, it's good to just deal with the units. What do you need to do with these values to get the units to work out, right? So we're really trying to get, pulses per degree. So how do we need to, arrange these so that everything cancels out? So, revolutions cancels out, steps cancels out, and here we end up with pulses per degree is 1600 divided by 360. So pretty easy. You don't have to write it out this long way, of course, but basically know that that's the conversion rate for our step. So if we want to, if our function for moving the stepper motor is calling for a float value of, we want to move 90 degrees, then we know that 90 degrees, we can use this conversion factor, right? So we can say pulses for 90 degrees, is equal to 1600 over 360 pulses per degree, and then times 90 degrees, right? Okay, so there, the degrees cancel out, and we're left with 1600 times 90 divided by 360, or you can say 90 over 360 is 1 over 4, right? So that equals 400 pulses. Okay, so that's the math we're going to be doing inside the code to calculate how many of these pulses. So that's one aspect, and what I really want to do here is create a function where we can move in a certain direction with a certain speed and a certain number of degrees, right? So we'll create a function, something like stepper move, and we're going to send it, degrees of rotation, speed, and direction. Okay, so we need to be able to calculate or convert all these commands into numbers of pulses, as well as our clock settings, or more specifically our ARR setting, so that we can control this rate of pulses, right? So this is going to be some P rate, right? Pulse rate, or pulse period, is going to be controlled by that ARR, right? So that's going to be a particular pulse rate, and by adjusting this ARR, down or up, we can control that delta T, and that's going to basically impact our speed, right? Because each one of these pulses is going to move it a little bit. So if we have pulses per second, that's going to give us degrees per second. And then direction is really going to be simple. It's just a GPIO output on the microcontroller that's feeding into that direction input on the driver. So that one will be the simplest implementation. Okay, so let's talk about calculating speed. Again, we can use our units, like we did up here, to kind of come up with what we want for that. All right. So let's see what we want. So we want to calculate speed in, let's say, degree. Let's say our unit that we're going to feed this command is degrees per second. So let's say speed in degrees per second. What's that really a function of? Okay, so we start with degrees. We know there's 360 degrees in 1 revolution, right? And we know there's 1 revolution in 1600 pulses. Okay. We also know there's, you know, one revolution or one pulse for one period, right? ARR or for one timer period. So this pulse rate, you know, this is going to be one ARR period, right? So as this ARR goes up, that's going to create this pulse, right? So we have one pulse per period of our clock or our timer, okay? And then we have one period corresponds to a certain number of ARR counts, right? So we have, so this period corresponds to a certain number of ARR counts. Okay, and then we have a certain number of ARR or counts per second, which is going to be the clock rate, right? So we have counter clock, counter clock counts per second. Okay, so counter clock counts, right, is this right here. It's our bus clock divided by our prescaler. So for this, I'm going to go ahead and just tell you what I'm using. You can set these to whatever is best for your application, but I'm going to use a, so the bus clock is typically going to be 12,500,000 counts per second, right? Or cycles per second. So I'm going to use a prescaler of, let's say, let's see, I want to get that down to something reasonable, maybe like 250,000. So what would that be? That would be maybe like 50 or 49, right? Let's pull up our calculator just to be sure. So we've got 12,500, and let's say we want to get it to like 250,000. Yeah, so ARR is going to be 50 minus 1, so 49. I mean, the PSC. So the prescaler is 49. Okay, so that means these clocks are going to be at 250,000, right? So we can go ahead and write that here. Okay, so here you can see you can calculate the speed in degrees per second. You know, given a certain number of ARR counts. That's really what we're trying to do, is we're trying to determine what's the speed of the stepper motor given this ARR setting, right? So if the ARR is lower, you know, we're going to have pulses happening faster, right? If the ARR is much higher, then we're going to have pulses, you know, moving, I think, more spread out, a longer period, and a lower, you know, pulse per second rate. Okay, so this whole equation right here we just kind of calculated is really what we're going to need to think about. But really we want to solve this for ARR counts, right? Because they're going to give us a speed in the command, and we need to be able to calculate or convert that to an ARR setting. And that's what we'll do, is when this command is issued, we'll need to calculate the ARR that gives us that speed. We can set the ARR, and then we can give the stepper a number of pulses at that rate, and that's going to give us the motion in the degrees we want, the number of degrees we want, and at the speed that we want. Okay. Okay, so if we want to solve this for ARR, you can see it's pretty simple. You just put ARR back over here, and then speed comes under here. And let's start a new page here, get some more room. Okay, so if we look at that, if we kind of condense that down and cancel out all the units we don't need, we really have degrees per second. This is speed is equal to 360 times 250,000 divided by ARR times 1600. Okay, so then we can just solve that for ARR, and we get the ARR value is going to be equal to 360 times 250,000 over the desired speed times 1600. Okay, so that's what we'll actually implement in our function when we want to calculate the ARR needed to have the stepper motor travel at a certain speed. This is going to set the rate of pulses. Okay, and so then we're looking at just controlling the rate of the pulses and then the number of pulses, right? So, you know, pulses is going to be, we calculated that before, right? If we want to go at 1600 pulses per degree, so, or per 360 degrees. Oh, like that. Okay, so these are the two, basically the main two calculations we're going to have to calculate when we want to make the stepper motor move. We need number of pulses, and we need that ARR auto reload register for the timer so that we can set the speed of the pulses. Okay. All right. So that's really the main calculations we need to do in this code. So let's go ahead and start writing the code. So what do we need for this? We're going to need a timer that can basically send out pulses. I'm going to use timer 2 in PWM mode. And that's going to be able, that's just one way to generate pulses. You know, you could use other timers, you could use output compare mode. And we'll just kind of, you know, even though the PWM rate will be pretty much staying the same, we're just going to be adjusting the period, right? So we're really not using PWM per se, we're just using it to generate pulses, which is fine. It's a good application for that because all you have to do is control the ARR to change that pulse rate. Okay, if you wanted to like output the rate or any other information, you know, you could also enable USART2. I'm not going to do that in this video, but you could easily, you know, use a printf statement to your console if you wanted to real-time show, you know, your calculations, or if you wanted to real-time show what the actual angle of the stepper motor was. You know, that would all be pretty easy to do as a small modification of this program. Okay. All right, so let's start some code. So I've already done this project, so I'm going to do it again just so you can see the whole process. So I have something called stepper demo that I already did. That's how I got the hardware working before. So hopefully we'll go through this and it'll also work. If not, I may need to go back and see what I did wrong. So let's start a new project. Okay, so I'm going to call this stepper, let's call it stepper example. Just make it different from my previous one. Okay, so I'm going to use STM32Cube. Everything else here can be default. And I always hit, well, I like to hit no here, especially if we're using timer clocks. There's a lot of clock modes that can get enabled, as we've seen, that can cause some issues. All right, so the IDE is getting this project directory all ready for us. Okay, so like we said, we're going to use timer 2, and we're going to use PWM mode. So I'm just going to choose channel 1, PWM. I told you the prescaler we're going to use, which is 49. And the counter period is something that will be varying, you know. So we can put in, I don't know, we can keep it like that for now. Since we'll be actually setting that before we really do anything with this timer, we can leave that period what it is. The pulse value, that's something we need to think about in numbers of counts. So we kind of need to know a range of what we're going to be dealing with, right? So we want to set this pulse value so that you know, we have a reasonable pulse width for the period that we're going to be generating, right? So I think I said the clock counts are going to be 250,000. So we're going to be varying that. So what is that in time? Let's say 250,000 pulses per second. Yeah, that's pretty quick, right? That's 4 microseconds per pulse. And then let's say we had 1,600 of these. Yeah, that would be a 0.064, you know, basically 6 milliseconds per rotation. That would be way too fast. I don't think a stepper motor could actually do that. So we're probably looking at, you know, something on the order of maybe, you know, maybe 1,000 times that, right? A fraction of a second, or maybe 100 times that, right? So 100 times that would be, you know, half a second per rotation. You know, that's kind of on the order of what we're looking at. Okay, so we're looking at maybe like, you know, setting the ARR to be maybe 100, you know, a factor of 100. So instead of being 250,000, we're gonna be looking at maybe, you know, maybe divide that down to maybe 2,500. Okay, so something like that. So you know, a good pulse value for that, you know, might be, you know, 100 or a couple hundred counts. So let's go ahead and just set to like, let's say like maybe 500 counts, just so that would give us a 20% duty cycle. But that's kind of limit, you know, once you're lower end, right? So your ARR can really only go down to what your pulse is, and then you don't really have pulses anymore, right? So that's going to be kind of the lower limit of your ARR, which is going to be kind of the upper limit of your speed, right? So you can kind of calculate how many counts that limit is and what that translates to actual speed. So you might have to play with that. You know, you really need to kind of think about what's the actual range of speeds you want to have in this thing. And for me, this is just an example, so I'm not going to get too exact. But you know, I would think you'd want something, you know, on the order of, you know, maybe 5 revolutions per second is moving pretty fast for a stepper, I would think, right? So maybe that's an upper limit, and then a lower limit. You know, really that would be limited by our total period. So that could be actually pretty long. So we can have this thing go as slow as we want, and then we're going to be kind of up against the limits of the actual stepper motor itself. So I think this will work for. So let's use a pulse value of maybe, say, let's use 499. You could always reduce that because that pulse can be pretty skinny going to the driver. But if you really want to, you know, reduce that down, you could. Okay, so all that being said, I'm going to use a pulse of 499. If you wanted this thing to go faster, you wanted pulses to come at a faster rate than that, then you could, you know, reduce this down somewhat. Okay. Our PWM mode 1. We do want an interrupt for this, right? Because this is, we want to know when these pulses are complete because we want to count them. Because we're going to need to count the numbers of pulses that have been sent to the stepper so that we can track how far it's moved, and we can stop the pulses when we've moved as far as we want to move. Okay, so we need to enable the interrupt. And like I said, if you wanted to enable the USART, you could. I'm not going to in this example, but you could. And I'm going to use one of the LED GPIO outputs, like PD15, say the blue LED, to control direction. So I do that just because it's already set up by default in the system. If you go to System Core GPIO, it's already got the 4 LEDs already defined by default. So no extra setup is needed, and it gives you a little bit of a visual indication. You know, you can see that LED go on and off as you're changing direction. So really, all I'm going to enable here is timer 2 for this example. Okay, so let's just verify our clock real quick. Okay, so we do have, if you select no on the default peripherals, it should load up this configuration, which is using the internal clock with all these default parameters, and you don't have to worry about this weird clock down here, and everything comes out to about 12.5 megahertz for the APB1 timer, okay, for the lower speed timers, which is what we used in our calculation, right, 12.5 megahertz. Okay, so everything looks good there, so I'm going to generate code. And not a whole lot of stuff we have to do here. We need to define some global variables, write a couple functions, and then you know, insert those calculations where they need to go. All right, so stepper example, let's go down to the main.c. Okay. All right, so this has already got the GPO and the timer 2 things set up for us. We're going to need some private variables. So we're going to need to track the number of pulses, and that I'm going to make that a global variable because it's going to be kind of done inside functions. We're going to be using that possibly in multiple functions. So I'm going to create a variable here. I'm going to call it pulse count. Okay, so that's just going to track the number of pulses for a command. So we give a command to move a certain number of degrees, and this is really the pulse. We're going to be counting the pulses, knowing how far, you know, or how many pulses we need to make it move a certain number of degrees. This will be that value that we'll track. Okay, and we can create another value, and this is going to be the basically the desired number of pulses. And I'll just, well, let's just leave that uninitialized for now, because that's what we'll be setting. When we issue a command, we'll calculate desired pulses, and then we'll move the stepper until that pulse count equals the number of pulses. Okay, and we're going to create a couple functions here. We're going to call one stepper move, and this is one that we want to basically tell it how far we want to move, at what rate, in what direction, right? So for degrees, I'm going to go ahead and use float, because, you know, I mean, there's a possibility you'd want to do this in fractions of a degree. I don't want to limit it to just being integers. Since we're doing those calculations, we're going to be doing the calculations in terms of float anyway. So we might as well give us that flexibility. And then, of course, at the very end, we're going to need to kind of round to a integer number of pulses and an integer ARR register value, right? So we can do all this stuff in float, and then we'll just have to round that to an integer at the end. So we're going to command numbers of degrees. We're going to command a speed. That can be defined however we want. And I think we called it degrees per second in our math. And then we'll just have a direction. Okay, so we can clockwise or counterclockwise. This will basically be a 0 or a 1, indicating a, you know, a certain direction. Okay, so we're going to need one more function here, and this comes down to, when we command this thing to move, um, we're going to start counting pulses. So we're going to be issuing a callback function every pulse, updating the pulse count, and then kind of comparing that to the desired pulses to see if we've issued the number of pulses we want. But the main program is still going to be running during this time, right? That while loop's going to be processing, even while this thing is going off, and these interrupts are keeping track of if our timer has moved or our stepper has moved far enough. So what we don't want to do is issue another command before the stepper has finished moving, because if it's not done moving, then we're going to kind of reset that whole process, and we won't travel the full distance we need. So a lot of different ways you can implement this, but I'm just going to have basically what I'm going to call a move delay that we can use in between commands. Just so after we issue a command, we can delay a certain amount based on how we can calculate how long it's going to take for the stepper to do what we commanded, and then we can, after that amount of time, we can issue the next command. So that just prevents the commands from stepping on each other. So for the move delay, we need to know basically the number of degrees we're moving and the speed. Okay, and then we also can set, like, if you do that exactly, you don't want to issue the next command exactly, because you might have a little bit of, you want a little bit of buffer there, a little bit of safety in between the commands, right? So we can, so I'm going to have like a pause, just a pause we can add on top of that. So degrees and speed is going to be used to calculate how long we think it's going to take for the stepper to move, and then we're going to add a little bit of in milliseconds, maybe a quarter of a second, just between commands, just to give a little bit of extra delay. Okay, so that's the two functions we're going to need to write. So we'll save our main for our while loop for the end. We're not going to issue the timer start yet, so the timer will start when we issue this stepper move. So that's the kind of the flow, is we'll issue this stepper move command. We'll do some calculations on the number of pulses we need and the ARR value we need to get the distance and angle and the speed. Then we'll start the timer with those parameters. And in the callback function for the timer, for each pulse, then we can increment the pulse count and compare it to desired pulse. And whenever the number of pulses equals the desired pulses, then we can stop the timer. And that means the motor has moved that distance and in that speed. Okay, so that's kind of the approach here. All right, so everything else should be set. Let's go down to user code 4, and we can implement our actual functions here. Okay, so the first one we'll do is our, let's do our stepper move command. Okay, and let's just go ahead and copy that from the prototype, just so we get everything straight. Okay. Okay, so let's do the easiest thing first, and that's going to be direction. So really, direction is going to be a 1 or a 0. We can define that however we want. Depending on the polarity you have it wired up to the driver. So you can change this depending on if you want a 0 to be clockwise or a 0 to be counterclockwise. I'm just going to leave it. I don't really care which way it is, but normally you'd want to actually plan for that. But I'm just going to set that pin value equal to 0 or 1 based on this command. So let's do a write. We know this is GPIOD. I'm using the blue LED, which is pin 15. So GPIO pin 15, and then this pin state I'm just going to make equal to direction. But you'll notice that this is an 8-bit unsigned integer. Really, we're giving the pin, a single bit value. So I just want to make sure this is a 1-bit. In case maybe by accident someone puts, a larger value in direction than 0 or 1, You know, maybe they put a different, you know, integer. I don't want to try to set, you know, pin state to something that's not a bit. So I'm just gonna do kind of an AND operation here, a bitwise AND, just to kind of strip off that first bit, if that makes sense. Just as a little bit of safety. It probably wouldn't matter anyway. I think if you had a larger value in here than 1 bit, it would probably just strip that down to this, you know, the bit, least significant bit anyway. Okay, so that's going to set the direction. So that's going to write to that GPIO pin, which is driving the direction input on the driver. Okay. All right, so now we need to calculate a couple things, a number of the desired pulses, and we need to calculate the ARR value, right? So let's do the ARR first. This is going to be the speed. And this is a 32-bit setting, right, in our timer for timer 2. So let's define a value ARR, and we showed this calculation before. Remember, it's going to be 3600 or 360, sorry, times 250,000, and then divided by 1600 times, and then the desired speed, which comes in as an input to the function, right? Okay. So that's the ARR, and then -1, right? Because the ARR, remember, is going to be that value -1. Okay, so one thing we need to think about here, though, is this is a 32-bit unsigned integer, right? Here we have a bunch of math over here, so speed is a float, so we need to make sure that this is all being calculated as a float. So I'm going to typecast this calculation as float, okay? And then I'm going to wrap all this thing like this, and then I'm going to have the final typecast the final calculation. So all this stuff will be done as float, and then I want this final one to be unsigned integer 32. Okay, so it'll match what's on the left, if that makes sense. Okay. So I said there's a syntax error. What did I do here? Oh, we're missing a parenthesis. Okay. All right, so it won't treat these as integers. This float typecast just means we're going to treat these as float. So we'll have float divided by float. I think this 1600 is automatically promoted to float because it's being multiplied by a float. So all this should be in float. We'll get some fraction or some you know, float type result here. Subtract 1, and then we'll typecast that to a 32-bit integer. That's kind of, you know, our rounding, and then we'll basically assign that to our ARR value. Okay. Now we need to calculate our desired number of pulses. This was a global variable we defined up above. This is also a integer, so we're going to typecast some result here. And remember, our calculation for that was degrees divided by 360 times 1600. That's going to give us our number of pulses. Okay. Okay. So if we wanted 360 degrees, that would give us 360 divided by 360 would be 1 times 1600. Okay, so I think that's all the calculations we really need to determine the period of our pulses and the number of pulses, right? So now we need to actually set a timer with those values. Okay, so let's do the ARR first. So we know our timer is, we have a handle set up for that, and we have, although the timer has already been initialized with some default values up at the very top, we have our timer to init. You know, we're going to actually reinitialize that once we know what ARR we want. So we're really going to be changing this initialization structure, right? So in timer 2, here's where we have the initialization, and you can see here we're setting this period right here. So really this is the element of the structure we're going to update with our ARR value, and then we can actually, you know, reissue this initialization command. So we can change how that timer is initialized. So handle of the timer, we're going to access the member elements, initialization, and then period. Okay, and you could change the prescaler here if you wanted. You could change any aspect of the timer, but we're basically going to set that period to our ARR that we just calculated. Okay, and then we need to initialize that timer again. How timer PWM init, and we'll use timer 2. Okay, so now our timer is reinitialized, the same structure it had before, so everything else is set the same except we just changed the ARR, you know, the period in that structure. Okay, so we have our desired pulses calculated. Now we just need to basically start the timer. Okay, so this is going to start the timer, which will generate pulses, which we're going to have driving the driver. So this would start the stepper actually moving. So PWM, we want to start with interrupt. Okay, this will be timer 2 and channel 1, right? So timer channel 1. Okay, so I think that function looks complete. We'll do our calculations, we'll set the timer period, and we'll kick it off. So now what's going to happen is every time we get a pulse, generate a pulse in timer 2, you know, there's going to be a lot of callback functions or a lot of interrupts happening. We selected the global interrupt for timer 2, so that's already being processed. You know, if we were to go into the it.c, we should see the timer 2 interrupt handler right here, and it's calling the driver IRQ handler, and then that is going to be what issues the callback functions for different events that trigger the global interrupt. So for ours, we need to go find out what's that event called that we need to add a callback function for. Okay, so let's go into the driver. If we're not sure, we can always go look it up. Go to the timer driver. Here's all the APIs, but if you scroll down a little bit further, you get a list of all the callback functions. Okay, so these are all the callback functions that can be issued based on events that trigger that timer global interrupt. So here you can see there's lots of callbacks. We're dealing with PWM mode, so here's like some MSP init. Once things are initialized, you get a callback. You can get a callback. But really what we're looking for here is this PWM pulse finished callback. So it's kind of like the same thing as this period elapsed, right? For just a basic timer, remember that's the period elapsed. But here, basically the equivalent for PWM mode is this PWM pulsed finished callback. So that just means it means that one period of the PWM mode pulse has been finished. So this is really the callback function that we want to use in PWM mode that's going to be triggered every pulse. So this is how we're going to count pulses, is in this callback function. We'll just increment that pulse variable and compare it to the number of desired pulses, and when it reaches that, we'll stop the timer, and that's how we'll control how many pulses are delivered to the driver and how far the stepper motor is going to move. So I'm going to do Control F here. Little trick, you can highlight something here and just hit Control F. It automatically populates it in Find. Click through here until we actually get to the actual prototype. Then we can copy the prototype. So right there. Okay. So let's do this, and we're going to put this callback function in our main.c. Remember, this is a weak implementation in the driver, and it's kind of unused, right? So this is just to keep the compiler happy, prevent unused arguments, compiler warning. But when we actually issue this callback function in our code, it's going to overwrite this weak implementation, and this will basically be ignored. So let's go up here to main. Okay, so really, a couple things we want to do here. You know, it's good practice. We know we're only using one timer, but you know, if you added a timer, you'd want to make sure you differentiate between the two. So it's good practice to go ahead and just say, if the timer returned is equal to timer 2, then we'll take action. If you had different channels or different timers, you know, you can actually expand this if to be if timer 2 and if channel 1. You could differentiate there. I'm just going to stop here at differentiating just for the timer itself. Sometimes it's kind of confusing to know what to put in here. You know, this is going to be an actual timer handle, right? So what's a timer handle actually consist of? Well, the timer actually in memory, this structure starts at the address of htimer2, right? So we created this htimer2 handle, and that is going to be a memory location where this structure exists, this htime2 that we populate up here, right? So we define htime2 right here, right? And then we populate that structure. So that actually exists in memory. If you go look up, you know, where that variable is in memory, it's going to be a certain location in RAM, right? So when we populate structure, you know, this is a structure in RAM, and we're, you know, assigning numbers to all these different member elements. So hTime2, this whole structure is going to be the address of the whole handle, right? So you could do other things where you're looking and see if htime.instance equals timer2. I think that's one way you could do it. So there's several ways to do this. I just like to do it like this because it's pretty straightforward. Whatever it's sending me back is going to have some address associated with it, right? If it's it's going to be the address associated with that structure. Okay. I think you could probably also do if htimer instance equals, you know, timer2 or something like that would probably work as well. I like to do it like that. Either way. Okay, so now we know we're only processing this section of code if the callback function was issued due to our PWM timer. Okay, so now we're going to basically let's say we're going to increment the pulse counter. Okay, so each time we get this, we know we've had one pulse. So we're going to increment the pulse counter, and then we're going to basically test if pulse count, and I'm going to say greater than or equal to desired pulses. You could say equal. I'm going to use greater than or equal to just because it makes me feel a little bit better inside. Okay, so if we've met our pulse count, that means the stepper motor is moved as far as we want, and now we can stop that timer, right? HAL timer PWM stop IT mode, and that's going to be htimer2 and timer channel 1. Okay, so if our pulse count matches our desired pulses, we know that the number of pulses have been issued to the driver to cause the stepper motor to move the distance that we wanted, right? So we don't need the timer anymore. Still stop the timer, and here we'll reset the pulse count. Right, so we're ready for the next command. So we've kind of initialized that pulse count. Okay, so I think that's all we need. Yeah. So if Pulse count does not, if it's less than desired pulses, this part won't be processed and we'll just be incrementing that pulse count each time. Okay, so I think that looks good. That should be all the functions. Oh, we have the delay function, right? Let's do that one. So let's copy this prototype. And we need to create a function that's going to give us a little bit of a delay. Okay, so the time it's going to take for this thing to move. So we have a speed, right? And basically we're going to well, let's look at this. Okay, so we want to know seconds, right? Time in seconds. Okay, so how are we going to calculate that? I think we have, we're telling it we want degrees per second in speed, right? And then we're also giving it degrees, right, of motion, of angle, right? So we're feeding it speed and distance, if you will, in angle, so we can use that to calculate time. And our delay, we're going to use the HAL delay command, which is in milliseconds. So we can say 1,000 milliseconds per second. Okay. All right. So the delay in milliseconds is going to be equal to speed times degree times 1,000. Wait, this is divided by degree. That doesn't work, does it? Yeah. Speed divided by degree times 1,000. Okay, so degrees per second divided by the number of degrees, and then times 1,000 milliseconds. That gives us this down here. Okay. All right, so speed divided by degree times 1,000. So that's pretty straightforward. Okay. So I'm just going to write this in one command, HAL delay and our delay is going to be, you can see up here, and it's a 32-bit unsigned integer. So let's go ahead and typecast whatever we calculate to that, just so we're not causing any issues. We're going to do this, calculate this in float. So I'm going to typecast the calculation as float, 1,000 times degrees divided by speed, which is what we just calculated. Okay, so that would be the delay. Is that right? No, parentheses aren't working out. Yeah. Okay. Now we also have this pause we need to add in here. So once we get the milliseconds, we think it's actually going to move, we're going to add some more milliseconds just to give us a little bit of buffer. Okay. All right, and then so we'll do the calculation. Then all that will get typecast to a 32-bit unsigned integer, and that should be, a number of milliseconds that it's going to take for the stepper motor to move, plus give a short pause. Okay. All right, so I think we've got all the content in here. Let's build and see if there's anything we need to address. Okay, we do have some errors. Let's see. What do we do here? Doesn't like our desired pulses. let's do desired pulses. Okay, so my original variable, I had pulse. I'm going to make that pulses, so that matches what I have here and everywhere else. Let's see if that fixes that. Okay, I got rid of all the errors, so we should be good to go. So now we just need to add some commands into maybe our infinite while loop so that we can make this thing actually move. Okay. All right, so what I did before was just issued a series of commands. So I think I did 90 degrees at 90 degrees per second. So it'll take 1 second basically to move that 90 degrees. Direction of 0. Now I need to basically call that delay function so we can wait for that move to happen. So the same parameters of degrees and rate. And then I'm going to add a quarter of a second, basically 250 microseconds, just to give a little bit of pause between those moves. Okay, so I think I did a series of 4 moves. Okay, and the next one was, so I moved 90, then I moved 180. I did that really fast at 1800 degrees per second in the other direction. Okay, and then I moved 135 degrees, about half that rate, 900 degrees per second. And then I returned back to our starting point, 45 degrees at 500 degrees per second, so a little slower. And this was 1. So alternating directions here. Okay, so just a series of moves, just to kind of demonstrate the concept. You know, this maybe isn't the most efficient way to do the move and the delay, but you know, you could put this delay maybe inside the function here, right? This stepper move. You know, maybe we could put the delay here inside that, and we have all the data we need to calculate that. So that might be a little bit of an efficient method. That way the program execution would kind of halt here. I think it would still process all these pulses. So I think it would still work, you know, the same way. But, you know, you could try that. That would be a little bit cleaner way to do this, right? Is to move that into that stepper move function. That way we don't have to reissue some of these numbers, you know, the duplicative numbers. Okay, so let's build this, and I'm going to try it out, and we'll see if it works. Okay, so I tried it and it did not work. So I took a couple of minutes to look at it, and I realized I did make an error. Maybe you caught it. I kind of glanced over it a little bit, but you know, the math here doesn't quite work out for this pulse. This pulse is way too high, so I think that's causing the issue. So when I try to move fast, and we try to have these pulses coming fast, let's calculate what the period of the pulse is. So the fastest thing I'm issuing is, let's say, 1800 degrees per second. Okay, so we're trying to move at 1800 degrees per second. So let's look at what that ARR value actually is. So let's just do a quick calculation. So we have 360 times 250,000, okay, divided by 1600, and then we wanted to move, what did I say, 1800 degrees per second. So that's going to give an ARR of 31.25. So you can see we had our pulse set up to actually Then we had our pulse set to 499. So this obviously wouldn't work. You try to move fast, you're not going to have a pulse because your pulse is longer than your period. So we actually need to put a pulse value. If this is maybe to the max speed we want to move, the pulse is going to need to be less than this. So let's change our pulse to 9 so that we'll have a pulse width of 10 counts. So if we go back up to our, let's do it in the IOC so that it'll save it. So timer 2. So I think what happened was my initial example, I went ahead and set this just to 499 just to give an initial period to it, even though we're going to be changing this for each command. But this pulse value is what needs to be, let's say 9. That way, when we change this to be a period of 31, you know, we have to have something less than that as our pulse. So 9 should be sufficient for that. So let's build this code again. Hopefully it doesn't overwrite anything. Still have our functions, our variables, our prototypes, and our, okay. So let's run this. So right now the driver is only moving the stepper for the very slow, I think this first one, this 90 degree, that's the only one that has a period that's longer than that 499. Okay, so now the stepper is actually moving how we want. Okay, so that fixed that problem. So, you know, you kind of need to look at your, you know, what's your max speed going to be? And that's where you need to really adjust your prescaler so that you get an ARR that's, you know, a value that's large enough to have a reasonable pulse value. You know, obviously at your highest speed, if your ARR is 1 or 2, that's going to be kind of an issue. You know, you need a little bit more resolution to give some sort of a pulse instead of just you know, a constant high level or whatever. So think about how fast you actually want to move. That's going to drive your minimum ARR count value, right? Because that's going to be your fastest move. And then you need to set your prescaler such that that value and pulse value, you know, kind of makes sense so that you know, you actually have a pulse. So, you know, there's a lot of things to think of when you think about what is your actual application going to be. Also, you know, the slowest you want to move could be an impact too, because obviously that period is going to have a maximum value determined by, you know, 16 or 32 bits, which is actually a pretty large number, but you know, that's going to also be the slowest you can issue pulses. So not usually going to be limited on that end, but something you need to think about. Your prescaler, you know, could impact that as well. So you need to, you know, think of a reasonable prescale value that'll give you, you know, some values that are within the window of what you intend to operate. Okay, so hopefully that was useful. Just one example of one way to do stepper motors. There's other ways to do this. The timers do have what's called a one pulse mode, and you could just tell the timer go issue a pulse. That's another way to do it instead of having it just pre-run in PWM mode and then counting those pulses. This is a little bit more straightforward to me, and also is a kind of an extension of what we've already done in PWM mode. So that's why I use this particular method. But anyway, hopefully this was useful, and let me know if you have any questions, and feel free to, you know, code up this example and see if you can get it working. With you know, the stepper motor, I think I got 5 of those for a few dollars, you know, maybe 10 or 20 bucks on Amazon, so they're just a few dollars each. And then those drivers also are pretty cheap as well, so you can actually get this setup going, you know, for, you know, probably 20 bucks total at most. It's pretty easy to do. Okay, thanks.